Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 114, Flatten binary tree to linked list. This problem challenges us to transform a binary tree into a right-skewed linked list in place. Let's dive in and explore the solution step by step. In this problem, you are given the root of a binary tree, and your task is to transform it into what we call a linked list. But instead of creating a new linked list structure, you will modify the tree in place using the existing treeNode class. In this flattened structure, all the nodes should follow the order of a pre-ordered traversal of the original tree. That means we visit the root node first, then the left subtree, and finally the right subtree. Once flattened, each node's left pointer must always be null, and the right pointer will link to the next node in the pre-order sequence. The input to the problem is the root of the binary tree, where each node has three attributes: val for the node's value, left for the left child, and right for the right child. The output, however, isn't a new structure. You are required to modify the tree directly in place, so it becomes the flattened linked list. In other words, the function doesn't return anything, it directly transforms the input tree as described. Let's look at an example to understand this better. Here's a binary tree with root node 1. The left child of 1 is 2, and the right child is 5. The left subtree of node 2 consists of nodes 3 and 4, while the right subtree of node 5 contains just node 6. After flattening this tree, the result will be a linked list where the sequence follows a pre-ordered traversal. Starting from the root, we encounter node 1, then move to the left subtree, visiting nodes 2, 3, and 4 in that order. Finally, we visit the right subtree with nodes 5 and 6. Notice how the left child of every node is null, and the right child connects to the next node in the sequence. This is the structure we aim to achieve. Here's another example that demonstrates the transformation. In this case, the input tree has only two nodes, 0 is the root, and 1 is the right child. The output linked list is similar to the input structure because the tree is already linear. Node 0 remains the root, and its left child is null. The right child points to node 1, which is the next node in the sequence. Since this tree already follows the pre-ordered traversal order, no further changes are required apart from ensuring the left pointers are null. This example highlights that some trees may already be in the desired shape and need minimal adjustment. Next, consider a tree with a slightly different configuration. Here, the root node is 1, and it has only a left child, node 2. To flatten this tree, we must ensure that the left child of node 1 becomes null and the right child points to node 2. The result is a linked list where node 1 is followed by node 2, both connected through the right pointers. This example shows how even a partially skewed tree can be transformed into the desired linked list structure by rearranging the child pointers appropriately. Finally, let's discuss some important edge cases to keep in mind. First, if the tree is empty, meaning the root is null, there is nothing to flatten, and you can simply return. For a single node tree, no changes are needed since it's already a valid linked list. In the case of a left-skewed tree, where all nodes have only left children, flattening will involve moving all nodes sequentially to the right child, nullifying the left pointers as you go. Meanwhile, a right-skewed tree is already flattened and requires no modifications. Lastly, for very large trees with up to 10 to the power of 4 nodes, your solution must be efficient and operate within the given constraints. This ensures it handles all edge cases and performs well even for the upper limit of input size. To tackle the problem of flattening a binary tree into a right-skewed linked list, we need to ensure that the transformation is done in place. This means using the existing structure of the treeNode class, where the right pointer connects to the next node in the sequence and the left pointer is always set to null. One approach we could consider is the brute force method, which relies on a simple intuition. The flattened tree essentially represents a pre-ordered traversal of the original binary tree. Based on this, the process involves two main steps. First, perform a pre-ordered traversal and collect all the nodes in a list. Then, iterate through this list and reassign the right pointers to connect sequentially while setting the left pointers to null. While this method effectively produces the desired structure, it has a time complexity of O(n) for traversing and reconstructing the tree, and a space complexity of O(n) for storing the nodes in the list. This space usage violates the in-place constraint, which is a key requirement of the problem. The brute force method, while functional, does not satisfy the in-place requirement due to the extra space needed for storing nodes. To address this, we can turn to an optimized approach that uses a reverse postorder traversal to modify the tree in place. Here, the idea is to traverse the tree in reverse preorder order, which means processing the right subtree first, then the left subtree, and finally the root. During this traversal, we maintain a previous pointer to keep track of the previously processed node. For each node, we directly rewire the pointers. The right pointer is set to point to previous, and the left pointer is set to null. This ensures that the tree is progressively flattened as we move through the traversal. The process is implemented using a recursive function, and the time complexity remains O(n) as we visit each node once. The space complexity, however, is reduced to O(h), where h is the height of the tree, since we only use the recursion stack. This makes it significantly more efficient in terms of memory usage. One of the advantages of the recursive approach is its in-place nature, which uses only O(h) extra space for the recursion stack. However, if we want to avoid recursion altogether, we can use an iterative approach with a stack. This method is conceptually similar to the recursive approach but relies on an explicit stack to simulate the call stack. The key idea is to flatten the tree iteratively by pushing nodes in reverse preorder order, which means pushing the right child first, then the left child. This ensures that the left child is processed before the right, maintaining the desired order. During the process, we update each node's right pointer to the next node in sequence and set the left pointer to null. The algorithm involves initializing a stack with the root node, then repeatedly popping nodes from the stack, processing them, and pushing their children. Like the recursive method, this approach has a time complexity of O(n) for visiting all nodes and a space complexity of O(h) for the stack. It avoids recursion and provides a more iterative perspective while achieving similar performance. After considering the different approaches, the optimized recursive method using reverse postorder traversal is the preferred strategy. This method is elegant, efficient, and adheres to the in-place requirement by directly rewiring pointers during the traversal. The critical insight here is that the flattened tree follows a preorder sequence, and by processing the nodes in reverse order, starting from the rightmost node, we can ensure that the right pointers are set correctly in one traversal. Compared to the brute force approach, this method avoids using extra space to store nodes, making it more space efficient. While the iterative approach also avoids recursion, it requires careful stack management and can be less intuitive to implement. The recursive method strikes the right balance between simplicity and efficiency, leveraging the natural recursion mechanism to produce cleaner and more concise code. The trade-off is the O(h) space used by the recursion stack, which is generally acceptable unless the tree is highly unbalanced. Overall, this approach is the best choice for solving the problem effectively and efficiently. In this problem, we are tasked with transforming a binary tree into a right-skewed linked list in place. The key is to modify the tree so that the right pointer of each node points to the next node in a preorder traversal, while the left pointer is always set to null. To achieve this, we use a reverse postorder traversal strategy. This is a variation of postorder traversal where we process the right subtree first, followed by the left subtree, and then the root. This approach ensures that the transformation preserves the preorder sequence. We begin by defining a recursive function called Flatten. This function will process each node and rearrange its pointers step by step. To help manage this process, we use a global variable previous to keep track of the last processed node. Initially, previous is set to none. The base case for our recursion is simple: if the current node is none, we return immediately, which effectively skips over empty subtrees. Then, we proceed by recursively calling Flatten on the right subtree first, preparing it for the transformation. Next, we recursively call Flatten on the left subtree. This ensures that the left side is processed after the right side, adhering to the reverse postorder traversal pattern. Once both subtrees are processed, we can update the pointers of the current node. Specifically, the right pointer of the current node is set to the previous node, which represents the next node in the desired preorder sequence. Then, the left pointer of the current node is set to null, since the final structure requires no left children. Finally, we update previous to the current node, marking it as the most recently processed node. To initiate the transformation, we call Flatten on the root of the tree. This triggers the recursive process that cascades through the entire tree. The reverse postorder traversal is a key insight here, as it allows us to link nodes directly without needing extra storage or backtracking. This ensures the algorithm runs efficiently in O1 additional space, excluding the recursion stack. The result is a flattened tree that maintains the pre-order sequence, meeting the problem's requirements. The algorithm relies on the tree node structure, which is directly modified to achieve the transformation. No additional data structures are introduced, making the solution space efficient. The global variable previously plays a critical role by ensuring that nodes are correctly linked during traversal. From a complexity standpoint, the algorithm processes each node exactly once, resulting in a time complexity of O(n), where n is the total number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, as this accounts for the maximum depth of the recursion stack. This design efficiently handles edge cases as well. For example, if the tree is empty, the algorithm simply exits without performing any operations. For a single node tree, no pointers need to be adjusted, so the node remains unchanged. Even for highly skewed trees, whether left-leaning or right-leaning, the algorithm operates seamlessly, flattening the structure without any additional overhead. Let's consider an example to better understand the transformation process. We start with the input binary tree where the root is 1, with left and right subtrees. First, we process the right subtree rooted at 5. From there, we move to the right child, 6. Since 6 has no children, we update its pointers, both right and left are set to null, and previous is updated to 6. Back at node 5, we update its right pointer to 6 and set its left pointer to null. Now, previous is updated to 5. Returning to the root, we process the left subtree starting at node 2. First, we move to the right child, 4. As before, we update its pointers, right is set to 5, left is set to null, and previous is updated to 4. At node 2, we then process the left child, 3. After updating 3's pointers so that right points to 4 and left is null, previous becomes 3. Back at node 2, we set its right to 3, left to null, and update previous to 2. Finally, at the root, we set right to 2, left to null, and previous to 1. The tree is now flattened into a linked list, 1-2-3-4-5-6. This process can also be optimized with iterative techniques, such as using a stack or a tail pointer, to avoid recursion while preserving the same results. This Python implementation solves LeetCode problem number 114, flatten binary tree to linked list, by recursively transforming the binary tree into a right-skewed structure in place. Here's how it works. First, the treeNode class is defined to represent nodes of the binary tree, with val for the node's value and pointers left and right for its children. The solution class contains the flatten method, which performs the transformation. The flatten method uses a helper function, flatten_tree, to recursively process the tree. This function takes a node as input and returns the tail, last node, of the flattened subtree rooted at that node. If the node is none, it simply returns none since there's no subtree to process. The function first recursively flattens the left and right subtrees by calling flatten_tree on node.left and node.right. These calls ensure that the left and right subtrees are processed before the current node. If the current node has a non-empty left subtree, the function attaches the flattened left subtree to the right side of the current node. Specifically, the tail of the left subtree, left_tail, is linked to the start of the right subtree, and the left pointer of the current node is cleared, set to none, to conform to the linked list structure. Finally, the function returns the tail of the flattened subtree rooted at the current node. This tail is determined as the rightmost node of the right subtree if it exists, otherwise the rightmost node of the left subtree, or the current node itself if both subtrees are empty. The recursion ensures that all nodes are visited and processed in pre-order traversal, and the tree is transformed in place into a right-skewed linked list. The solution handles edge cases such as an empty tree, root is none, and trees with only one child, ensuring correctness and robustness in all scenarios. Here, we define the structure of a binary tree node using the treeNode class. Each node in the binary tree contains an integer value, a left child, and a right child. We provide two constructors for flexibility, one that initializes only the value, and another that initializes the value along with its left and right children. Next, we move on to the flatten method, which takes the root of the binary tree as input. This method serves as the entry point to our solution and calls a helper function, flatten tree, to perform the actual flattening process recursively. The flatten tree method starts by checking if the current node is null. If it is, we simply return null since there's nothing to process for an empty subtree. The flatten tree method then proceeds to recursively flatten the left and right subtrees by calling itself on the left and right children of the current node. After obtaining the tails of the flattened left and right subtrees, we check if a left subtree exists. If it does, we attach its tail to the right child of the current node, move the entire left subtree to the right side, and clear the left pointer by setting it to null. This effectively shifts the left subtree into the desired position in the flattened tree. Finally, the method returns the tail of the flattened tree, which is either the tail of the right subtree, the tail of the left subtree if the right subtree is null, or the current node if both subtrees are null. This ensures that the function works correctly for all cases, including leaf nodes. To begin solving this problem, let's start with a simple binary tree. The root node is 1, which has 2 children, 2 on the left and 5 on the right. Node 2 further has 2 children, 3 on the left and 4 on the right. Node 5 has only one right child, which is 6. The goal is to flatten this tree into a linked list in place, following the pre-ordered traversal order. First, we start at the root node, which is 1, and call the helper function flatten_tree1. This function will recursively traverse the tree. We begin by flattening the left subtree of node 1, which means we call flatten_tree2. Now at node 2, we further flatten its left subtree by calling flatten_tree3. Since node 3 has no children, it becomes the tail of this branch, and we return node 3. Next, back at node 2, we proceed to flatten its right subtree by calling flatten_tree4. Similarly, node 4 has no children, so it also becomes a tail and is returned. At this point, node 2 has flattened left and right subtrees. We merge them by attaching the tail of the left subtree, which is node 3, to the right of node 2. We then update node 2's right pointer to point to node 3. This completes the process of flattening node 2's subtrees. Now that node 2's subtrees are flattened, we clear its left pointer because the tree is being converted to a linked list format. At this point, node 2's right subtree ends with node 4, so we return node 4 as the tail. Back at the root node, 1, we proceed to flatten its right subtree by calling flatten_tree5. At node 5, the left subtree is already none, so we move directly to flattening its right subtree by calling flatten_tree6. Since node 6 has no children, it becomes the tail of node 5's right subtree, and we return node 6. With both subtrees of node 5 flattened, we find that there's no left subtree to merge, so the right subtree remains unchanged. The tail of node 5's flattened subtree is node 6, which we return. At this point, we return to the root node, 1, where we now merge its left and right subtrees. We attach the tail of the flattened left subtree, which is node 4, to the right of node 1. Then, we update node 1's right pointer to point to node 2, effectively linking the flattened left subtree to the root. Finally, we clear the left pointer of node 1 and return node 6 as the tail. The entire tree is now flattened into a linked list following the sequence 1, 2, 3, 4, 5, 6. In the second example, the binary tree contains only left subtrees. The root node is 1, which has a left child, 2. Node 2 also has a left child, 3. To flatten this tree, we start at the root, node 1, and call flatten_tree1. We first flatten the left subtree of node 1 by calling flatten_tree2. At node 2, we move further down to flatten its left subtree by calling flatten_tree3. Since node 3 has no children, it becomes the tail of this branch, and we return node 3. Back at node 2, we merge its left and right subtrees. We attach the tail of the left subtree, which is node 3, to the right of node 2. Then, we update node 2's right pointer to point to node 3 and clear its left pointer. Node 2's flattened subtree now ends with node 3, so we return node 3 as the tail. Finally, we return to the root node, 1, where we merge its left and right subtrees. We attach the tail of the flattened left subtree, which is node 3, to the right of node 1. Then, we update node 1's right pointer to point to node 2 and clear its left pointer. The tail of the entire tree is node 3, and the tree is now flattened into a linked list with the sequence 1, 2, 3. In the third example, the binary tree contains only right subtrees. The root node is 1, which has a right child, 2, and node 2 has a right child, 3. To flatten this tree, we start at the root node, 1, and call flatten_tree, 1. Since the left subtree of node 1 is none, we immediately return none for the left tail. Next, we flatten the right subtree of node 1 by calling flatten_tree, 2. At node 2, its left subtree is also none, so we return none for the left tail. We then flatten the right subtree of node 2 by calling flatten_tree, 3. Since node 3 has no children, it becomes the tail of node 2's right subtree, and we return node 3. At this point, node 2 has no left subtree to merge, so its right subtree remains unchanged, and we return node 3 as the tail. This completes the flattening of node 2's subtrees. Finally, we return to the root node, 1, where we merge its left and right subtrees. Since node 1 has no left subtree, there's nothing to attach or merge on the left. The right subtree remains as it is, and we return node 3 as the tail of the entire tree. The final flattened tree is already in the desired linked list format, with the sequence 1, 2, 3. This example demonstrates that when the tree already follows a right-skewed structure, the algorithm simply traverses and confirms the structure without making additional changes. The time complexity of this solution is O(n), where n represents the total number of nodes in the binary tree. This is because the algorithm processes each node exactly once through a post-order traversal, which follows the sequence of left subtree, right subtree, and then the root. For every node, the operations performed relinking its left subtree to its right and clearing its left pointer only take O(1) time. Since these constant time operations occur once for each of the n nodes, the total time complexity sums to O(n). Now, looking at space complexity, it is determined by the depth of the recursion stack. In a balanced binary tree, the height of the tree is O log n, leading to O log n space usage. However, in the worst case of a completely skewed tree, where all nodes are aligned linearly, the height becomes O(n), resulting in O(n) space. Importantly, no extra data structures are used beyond the recursion stack, so the overall space complexity aligns with the tree's height, O(h). Comparing this to a brute force approach helps highlight the efficiency of the current solution. A naive method would involve performing an in-order traversal to collect all the nodes in a separate list, followed by iterating through that list to relink them into a linked list. While the time complexity for this is also O(n), the auxiliary space required to store the list is O(n), which makes it less optimal. In contrast, the optimized solution achieves the transformation in place, eliminating the need for additional data structures and reducing the auxiliary space to just the recursion stack O(h). Time complexity remains O(n), since every node must still be visited. For best-case scenarios, such as a balanced binary tree, the height is O log n, leading to O(n) time on O log n space. For average cases, the analysis is similar to the best case. However, in the worst case of a completely skewed tree, the height grows to O(n), so time complexity remains O(n), but space usage increases to O(n). Mathematically, every node undergoes O(1) operations, and summing this across all nodes gives O(n) time. The recursion depth, proportional to the tree's height, determines the space complexity, which is O(h). When working on this problem, there are some common mistakes to watch out for. First, it's crucial to maintain in-place transformation. This means you should avoid creating new nodes or using auxiliary data structures, like lists, to store the flattened tree. Using such approaches violates the problem's constraints, as the goal is to reuse the existing tree node structure. Another mistake is ignoring the left subtree after flattening it. Once the left subtree is flattened, it must be connected to the right pointer of the current node, and the original right subtree should be moved to the end of the new flattened chain. Additionally, ensure your recursive base case is handled correctly. Forgetting to check for root == null can lead to infinite loops or null pointer exceptions, so always account for leaf nodes in null cases. Lastly, be mindful of inefficient traversal when appending the original right subtree. If you traverse the right chain naively in O(n) time during every step, the overall solution can degrade to O(n²). To prevent this, consider tracking the tail reference of the flattened subtree during recursion to optimize this step. Overcomplicating the solution can also be a pitfall. Some approaches try to handle too many edge cases individually, which makes the logic harder to follow. Instead, stick to a systematic plan, like post-order traversal, to simplify your implementation and ensure correctness. From an interview perspective, this problem is an excellent test of tree manipulation skills, particularly understanding different traversal orders such as pre-order and post-order. Post-order traversal is especially useful for problems like this, where bottom-up transformations are needed. It's also a great opportunity to demonstrate your ability to handle in-place constraints, a common requirement in both tree and linked list problems. Interviewers may ask follow-up questions about time and space complexity, so be ready to explain the differences between recursive solutions, which use O, n, space due to the call stack, and iterative solutions, which can achieve O, 1, space. Finally, don't forget to address edge cases, such as single-node trees, empty trees, or trees that only have left or right subtrees, to show you've considered all scenarios. This problem is closely related to several other tree manipulation challenges on LeetCode, which can help you strengthen your understanding of recursion and traversal. For instance, LeetCode 1008, which involves constructing a binary search tree from pre-order traversal, emphasizes the importance of pre-order traversal and recursive logic. LeetCode 617, on merging two binary trees, reinforces the concept of in-place updates, making it another relevant problem to practice. Similarly, LeetCode 105, which focuses on constructing a binary tree from pre-order and inner traversal, highlights techniques for reconstructing trees based on traversal orders. Lastly, LeetCode 226, where the task is to invert a binary tree, is a simpler modification problem that serves as good practice for recursive tree manipulation. Exploring these problems can deepen your understanding of the patterns and techniques required for this type of question. There are multiple approaches to solving this problem, each with its own advantages and trade-offs. The recursive post-order traversal approach is the most common and intuitive. It processes the tree in a bottom-up manner, ensuring that the left and right subtrees are flattened before handling the current node. However, this method uses O, n, space due to the recursion stack. Another option is the iterative approach using a stack, which simulates recursion by explicitly maintaining the order of nodes to process. This reduces space complexity to O1 if you ignore the stack space, but it does make the implementation slightly more complex. Finally, there's the Morris traversal, which uses the structure of the tree to perform the transformation without extra space. This achieves true O1 space complexity but is more challenging to implement and debug. Each approach has its strengths, so it's important to understand the trade-offs and choose the one that best fits the constraints and context of the problem. Great job working through this problem. We reviewed how to flatten a binary tree to a linked list using an efficient in-place algorithm. Remember the importance of tree traversal techniques and in-place optimizations. Thanks for watching, and stay tuned for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!